In this video, I'll show you how to perform and interpret Fisher's exact test in R. I'll also show you how to report the results in APA style. I'm working with RStudio, a program that makes it easier to work with R. I'll leave a link to the download page in the description in case you need it. Fisher's exact test is used to determine whether there is a significant relationship between two categorical variables, for example, between students' gender and their study mode, so whether they study part-time or full-time. It's typically used as an alternative to the chi-square test of independence when sample sizes are small and the variables are dichotomous. So I've already imported my data, but if you're not sure how to do this, you can pause this video and check out our tutorial on importing Excel data files into R. I have data from 20 fictitious students. The dataset for Fisher's exact test must include two categorical variables. In our example, these are gender and study mode. We want to determine whether there is a relationship between the student's gender and their study mode. If your dataset is formatted like mine, with each column representing a variable and each row representing a subject or record, you'll need to create a contingency table before you run Fisher's exact test in R. Contingency tables summarize the relationship between categorical variables. We can create one in R using the code on screen. You'll need to replace the highlighted text as follows. Contingency table, this is the name you give to your contingency table in R. Feel free to use another name if it is more meaningful to you. X and Y, the names of the two categorical variables. In our example, these are gender and mode, and it doesn't matter which variable is X and which is Y. DF, this is the data set that contains your variables, and the data set in our example is called study_mode. So the command for our example is on screen. I'll just type this in RStudio and then select the Enter key to execute the command. If we look at the Environment tab here on the top right of the screen, we can see that this new contingency table has been created. To display it, we just need to type the name of our contingency table and then select the Enter key on our keyboard. Here's a screenshot of the contingency table for our example. It displays the frequency of the students in our sample based on their gender and study mode, but to determine if there's a significant association between gender and study mode, we need to conduct a statistical test. So when should we use Fisher's exact test? To assess relationships between categorical variables, we often use the chi-square test of independence. However, this isn't appropriate if your data violates any of the assumptions of that test. In particular, the chi-square test requires that the expected frequencies in each cell be at least 5. To check this assumption in R, we need to generate a contingency table, not of actual frequencies like we've just done, but of expected frequencies. We can create one in R using the code on screen. If you didn't call your contingency table, you'll need to replace the highlighted text with the name of your table. Once we type the command and select the Enter key on our keyboard, we see the expected values for each combination of our variables in R. Here's a screenshot showing the expected values contingency table for our example. The expected frequencies for 2 of the cells in our table are less than 5, so our data violates one of the assumptions of the chi-square test of independence. R also gives us a warning message saying chi-squared approximation may be incorrect. So our data violates an assumption of the chi-square test, and that's where Fisher's exact test comes in. The next step then is to check that our data meets the assumptions of Fisher's exact test. When we use Fisher's exact test, we make the following assumptions. Both variables are categorical. Categorical variables include, for example, gender, nationality, and yes/no responses. The groups within each of your categorical variables are mutually exclusive. For example, students' mode of study cannot be both part-time and full-time. Independence of observations. None of the observations in the dataset is influenced by any of the other observations. For Fisher's exact test, a small sample size is okay, and expected values of less than 5 are okay. Now we can conduct Fisher's exact test in R using the command on screen. As before, if you gave your contingency table a different name, you'll need to replace the highlighted text with the name of your own contingency table. So I'll type this command into R and select the Enter key to execute it. Here's a screenshot of the output for our example. The most important value in our output is the p-value. A p-value that is less than or equal to the alpha level we have selected for the test indicates a significant relationship between the variables. It is common to select a significance level of 0.05. A p-value that is greater than the alpha level we have selected indicates that there is not a significant relationship between our variables. Since our p-value of 0.642 is greater than 0.05, we conclude that there's no significant relationship between gender and study mode. The results of our Fisher's exact test can be reported in APA style as you see on screen. We have a dedicated video on writing up the results of Fisher's exact test in APA style. I'll add a link below and in the cards. Well, that's it for this tutorial. If you'd prefer written instructions, please head over to our website at easysbss.com. And if you'd like to see more videos like this, please subscribe to our channel.